The alarm goes off at 6:30 in the morning. Not too early, not too late. Just early enough to beat the worst of the Seattle traffic. To arrive at the office before the flood of emails begins, before the morning stand-up, before the day truly starts. Maya Chen reaches over and silences her phone. For a moment, she lies still in the darkness of her bedroom, listening to the rain against the window. It's always raining in Seattle, or so it seems. 5 years since she moved here from California. 5 years of gray skies and drizzle, and the occasional brilliant summer day that reminds you why people endure the rest of it. She's been at Amazon for 3 years now, working as a data scientist on the personalization team, and she still hasn't gotten used to the rain. But she has gotten used to the rhythm of the work, the cadence of experiments and models and deployments. The satisfaction of seeing a tiny change in an algorithm ripple out to affect millions of customers. The knowledge that somewhere, right now, at this very moment, someone is clicking on a product recommendation that her model helped generate. Someone in Tokyo is buying a book. Someone in London is ordering kitchen supplies. Someone in Mumbai is adding electronics to their cart. And the system that suggested those products, that predicted those needs, that connected those customers to those items, that system has Maya's fingerprints all over it. That's the thing about working at Amazon. The scale is almost incomprehensible until you live with it for a while. Every single day, hundreds of millions of people visit the site. Not hundreds, not thousands, not even millions singular, hundreds of millions. Each one browsing, searching, clicking, adding to cart, purchasing, returning, reviewing. Every interaction generates data. Every click is recorded. Every second spent on a page is measured. Every scroll depth is tracked. The numbers become abstract after a while. Billions of interactions, trillions of data points, petabytes of storage, exabytes of data processed annually. Your brain can't really hold numbers that large. They become symbols rather than quantities. But somewhere in all that noise, there are signals, patterns, truths about human behavior that, if you can find them, if you can model them accurately, if you can turn them into code that executes in milliseconds and serves predictions in real time across a distributed global infrastructure, can move millions of dollars by dinner. Maya gets out of bed. Her apartment is small but comfortable. 1 bedroom in Capitol Hill. Walking distance to coffee shops and restaurants, though she rarely has time to enjoy them during the week. The bedroom is dark. She doesn't open the curtains, just navigates by the dim glow of her phone screen to the bathroom. She showers. The hot water helps wake her up, helps transition from sleep mode to work mode. She thinks about the day ahead, what's on her calendar, what experiments are running, what models need attention. There's always something. Always another optimization to try. Always another hypothesis to test. Always another data set to explore. After the shower, she gets dressed. Jeans and a sweater. Amazon's dress code is casual. No one cares what you wear as long as you deliver results. She goes to the kitchen, makes coffee in her French press. Strong and black. No sugar. No milk. Just caffeine and bitter comfort. While the coffee steeps, she checks her phone more carefully now. Opens Slack. The messages have been piling up since she went to sleep last night. Amazon operates globally, 24 hours a day, 7 days a week, 365 days a year. Someone is always working, always shipping code, always running experiments, always pushing forward. There are messages from colleagues in other time zones. Someone in Bangalore has a question about the model architecture. They're trying to replicate one of Maya's experiments and hitting an error. She makes a mental note to respond once she gets to the office where she has access to her full notes. Someone in London wants to discuss the results from yesterday's A/B test. The new ranking algorithm is showing promising results. Click-through rate is up 0.2%. Conversion rate up 0.1%. Small numbers, but meaningful at scale. She responds to the urgent messages, lets the others wait. This is a skill you develop quickly at Amazon. Email triage, message triage, information triage. There's too much to process everything. Too many channels, too many threads, too many people wanting your input or your time or your expertise. You learn to identify what matters and let the rest flow past like water around a stone. Maya drinks her coffee standing at the kitchen counter, looking out the window at the gray Seattle morning. The rain has stopped for now, but the streets are wet and shining. Cars pass by with their headlights still on. Pedestrians hurry along the sidewalks with umbrellas and rain jackets. Everyone moving with purpose, going somewhere, doing something. The city waking up. She rinses her coffee cup, grabs her backpack, checks that she has her laptop, her badge, her headphones. Then she's out the door, locking it behind her, down the stairs to the street, walking the 3 blocks to where she parks her car. The drive to Amazon's headquarters takes 25 minutes in morning traffic. She could take the bus, could bike, could walk even, though that would take close to an hour. But she likes having her car, likes the control, likes being able to leave when she wants, rather than being tied to a bus schedule. She merges onto the freeway, flows with the stream of headlights and taillights all moving in the same direction. All those people going to work, all those individual lives, all those separate stories, and somehow they all coordinate without central planning. Traffic is like a giant distributed system. Millions of independent agents making local decisions that somehow produce global patterns. It's not unlike what Maya does every day, building systems that coordinate millions of independent customer behaviors, predicting patterns, optimizing flows, trying to match supply with demand, trying to connect people with products, trying to minimize friction and maximize satisfaction. Amazon's headquarters in downtown Seattle. Multiple buildings now, whole city blocks, glass and steel towers with names like Doppler and Day One and Rufus, named after various Amazon traditions and inside jokes. Inside those buildings, tens of thousands of people working on everything from cloud computing infrastructure to retail operations to logistics to artificial intelligence to digital media to groceries to healthcare. The company has grown impossibly large. Started as an online bookstore in 1994. Now it's everything. Retail, AWS, Prime Video, Alexa, Whole Foods, Ring, Twitch, and somewhere in that vast organism, Maya has her role, her small but crucial part to play. She parks in the garage, level 3, walks to the elevator. Already there are dozens of other people converging, all wearing badges, all carrying laptops, all plugged into their phones. The elevator fills quickly. No one talks. Everyone is in their own world, checking email, reading Slack, reviewing documents. The doors close and they rise together in silence. Maya gets off at the 7th floor, badges through the security door, walks through corridors that smell like coffee and ambition and slightly stale air conditioning. The walls are decorated with leadership principles. Printed in large letters: customer obsession, ownership, invent and simplify, bias for action, learn and be curious, hire and develop the best, insist on the highest standards, think big. These aren't just slogans. They're not corporate jargon. They're the operating system, the cultural code that runs underneath everything else, the shared language that everyone speaks. In meetings, people cite the leadership principles. That's not very customer-obsessed. We need to think bigger here. Let's insist on the highest standards. It sounds cultish from the outside, but from the inside it provides clarity, a framework for making decisions, a way to resolve disagreements. When two people have different ideas about what to do, they can appeal to the principles. Which approach is more customer-obsessed? Which one shows more bias for action? It's not perfect, but it works better than most alternatives. Maya reaches her desk just before 8 o'clock in the morning. She's on the 7th floor, an open office layout, rows upon rows of desks with monitors and standing desk converters and people already hunched over keyboards, already deep in code or data or documents. The personalization team sits together, about 30 people, data scientists, machine learning engineers, product managers, software developers, technical program managers, all focused on the same goal, helping customers discover products they'll love. The work breaks down into different areas. Some people work on the homepage recommendations, those prominent boxes that show you suggested products the moment you land on Amazon.com. Others work on search ranking, making sure when you search for wireless headphones, you get the most relevant results at the top. Others work on post-purchase recommendations, the emails that say, "You might also like these items." Others work on the product detail page recommendations, the frequently bought together. And customers who bought this also bought modules. Maya works primarily on the frequently bought together module. It appears on product pages, shows you items that other customers commonly purchase in combination. If you're looking at a camera, it might suggest a memory card and a camera bag. If you're looking at a textbook, it might suggest a study guide and highlighters. The goal is to make it easy for customers to find complementary products, to create bundles, to increase basket size while genuinely helping people find what they need. It sounds simple, but at Amazon's scale, nothing is simple. The product catalog has hundreds of millions of items. The number of possible combinations is astronomical. You can't just compute all pairwise associations and store them. The storage alone would be prohibitive, and even if you could store them, the combinations change constantly. New products are added, old products go out of stock, customer preferences shift, seasonal patterns emerge and fade. So you need algorithms, smart algorithms, machine learning models that can generalize, that can learn patterns from historical data and apply them to new situations, that can make predictions in real time as customers browse the site, that can adapt as behavior changes, that can handle cold start problems when new products have no history, that can scale to serve millions of requests per second without breaking. Maya logs into her laptop, opens her email, 43 new messages since she left yesterday evening. She scans them quickly. Most can wait. But one catches her attention. It's from her manager, Rajesh. Subject line, model performance dip, need to investigate. Her stomach tightens slightly. Model performance dips are never good. They mean something in the system has changed, something unexpected, something the model wasn't trained to handle. User behavior has shifted. The data distribution has drifted. A competitor launched a promotion. A supply chain issue affected inventory. A bug was introduced in the code base. There are 1,000 things that can go wrong when you're operating at this scale. She opens the email. Rajesh has attached a link to a dashboard, one of the internal monitoring tools that tracks key metrics for all the personalization systems. Maya clicks through. The dashboard loads. Graphs and charts and numbers. Most of them are green, within expected bounds, but one metric is flagged red. Click-through rate for the frequently bought together module on product pages. The rate has declined by 0.3% over the last 48 hours. 0.3%. It sounds tiny, insignificant, a rounding error. But at Amazon's scale, 0.3% represents millions of dollars in lost revenue. Represents thousands of customers who didn't find the product they were looking for, who had a slightly worse shopping experience, who might have gone to a competitor instead. This is what data science at Amazon really means. It's not about building elegant algorithms in isolation. It's not about publishing papers at academic conferences or winning Kaggle competitions or impressing your peers with mathematical sophistication. It's about maintaining systems that operate at unimaginable scale, systems where tiny changes cascade into massive impacts, where every decimal point matters because it's multiplied by billions of interactions, where you're constantly fighting entropy and drift and the 1,000 natural shocks that complex systems are heir to. Maya pulls up the dashboard herself, starts drilling down into the data. The decline isn't uniform across all product categories. That's important. If it were uniform, it would suggest a systemic issue, maybe a code change, maybe an infrastructure problem. But it's not uniform. It's concentrated in specific categories: electronics, home and kitchen, tools and home improvement. The decline started around 8 p.m. on Monday evening. Interesting. Very interesting. What changed on Monday evening? Maya opens another browser tab, navigates to the internal wiki, searches for recent deployments, code changes, configuration updates. Nothing stands out. The usual stream of minor updates, bug fixes, performance optimizations. Nothing that should have affected the recommendation quality. She checks the product catalog. Were any major new products launched on Monday? She queries the database. Filters for products added to the catalog with high expected traffic. And there it is, a new smartphone, flagship model from a major manufacturer. Released on Monday evening, heavily promoted. Millions of customers visiting the product page, checking specs, reading reviews, comparing prices, adding to carts. Maya feels a hypothesis forming. She navigates to the product page for the new smartphone, looks at the frequently bought together recommendations. There are 4 suggested products: a phone case, a screen protector, a wireless charger, a set of earbuds. All reasonable suggestions, all items that customers frequently buy with smartphones. But wait, she clicks on the phone case, reads the description. It's designed for a different model, an older phone from the same manufacturer, different dimensions, different button placements. It won't fit the new phone at all. She checks the screen protector. Same problem, wrong size. She checks the wireless charger. This one is okay, universal compatibility. But then she looks at the earbuds. They have the old connector type, not compatible with the new phone. Now she sees the problem. The recommendation model is using collaborative filtering. It's looking at historical patterns. What did customers buy together in the past? The historical data shows that when people bought smartphones from this manufacturer, they often bought these accessories. So the model is recommending those accessories for the new phone. It's technically correct based on the patterns, but it's functionally wrong because the world has changed. The new phone has a different form factor, different ports, different requirements. This is a classic problem in machine learning: concept drift, distribution shift, covariate shift. The fundamental assumption underlying all machine learning is that the future will resemble the past, that the patterns you learn from historical data will continue to hold going forward. But that assumption breaks when something genuinely new happens, when a discontinuity occurs, when the rules change. And in a fast-moving business like consumer electronics, discontinuities happen all the time. New products launch, standards change, competitors innovate, customer preferences evolve. The model can't just learn static patterns. It has to adapt. It has to recognize when it's operating outside its training distribution. It has to have fallback strategies for handling novelty. Maya checks the time. 8:45. She has 15 minutes before the morning stand-up. Enough time to put together a preliminary analysis. She opens a Jupyter notebook. This is her primary working environment. A web-based interface where she can write Python code, execute it immediately, and see the results in line. It's perfect for exploratory data analysis. for poking around in datasets, for building and testing ideas iteratively. She writes a quick query to pull click-through rate data for the new smartphone's product page over the last week. The query goes to Amazon Redshift, the company's massive data warehouse, a distributed system capable of handling petabyte-scale analytical queries. The query takes about 90 seconds to execute, returns a table with hourly metrics. She plots the data. There's a clear drop starting Monday evening when the phone launched. Before that, the CTR was stable at around 3.5%. After the launch, it dropped to 2.1%, a decline of 1.4 percentage points, much bigger than the overall 0.3% decline Rajesh flagged. This product is an outlier, dragging down the overall numbers. She creates another visualization, a bar chart showing CTR by product category. Electronics shows the biggest decline. Makes sense. The new phone is in electronics. The problematic recommendations are affecting that category most. Home and kitchen shows a smaller decline. Tools shows an even smaller decline. As she digs deeper, she realizes those declines might be indirect effects. Customers who were browsing electronics products and clicked on the recommended new phone, then saw bad recommendations on the phone page. The spillover effect. The clock hits 9. Time for stand-up. Maya saves her notebook, grabs her laptop, heads to the small conference room where her team meets every morning. The room fills up quickly. 10 people today, 4 data scientists including Maya, 2 machine learning engineers, 1 product manager, 1 software developer, 1 technical program manager, 1 intern who just started last week. They gather around the table with their laptops and coffee cups. Some people are remote, dialing in via video conference, faces on the screen mounted on the wall. Rajesh leads the stand-up. He's been at Amazon for 7 years, started as an individual contributor, worked his way up to senior data scientist, then staff scientist, now manages a team of 10. He's good at it. Technical enough to understand the work, strategic enough to see the big picture, supportive enough to help when people are stuck, demanding enough to maintain high standards. Let's get started, Rajesh says. We'll go around the room. Remember, keep it brief. What you did yesterday, what you're doing today, any blockers. If something needs deeper discussion, we'll take it offline. Maya, you want to start? Sure, Maya says. Yesterday, I was working on feature engineering for the seasonal patterns project. Today, I'm investigating the CTR decline that you flagged. I looked into it this morning and I think I found the root cause. The new phone launch is showing incompatible accessories because our model is relying too heavily on historical patterns for that brand. I'll dig deeper and put together a more detailed analysis. Good, Rajesh nods. That's priority 1 today. We need to understand the full scope and come up with a fix. How confident are you in that diagnosis? Pretty confident, Maya says. The timing lines up. The affected categories line up. The specific product page shows clearly wrong recommendations. I need to quantify the revenue impact and think through the solution, but I'm 90% sure that's what's happening. Okay, keep me posted. Let's sync at noon to discuss. Rajesh moves on. Chen, you're next. Chen is one of the machine learning engineers. He's responsible for taking models from notebooks and deploying them to production, making them fast, making them reliable, making them scale. It's a different skill set from data science. Data scientists can be messy, can write code that works but isn't optimized. ML engineers need to think about latency, about throughput, about failure modes, about monitoring, about all the unglamorous but essential work of keeping systems running at scale. Yesterday, I was optimizing the inference pipeline for the search ranking model, Chen says. We're seeing some latency spikes during peak traffic. Today, I'm continuing that work. I need to profile the code more carefully to identify the bottleneck. No blockers right now. How are the latency numbers looking? Rajesh asks. Median is good, 50 milliseconds. But the 99th percentile is spiking to 200 milliseconds. That's unacceptable. We need to get it under 100. Agreed. Let me know if you need more compute resources. We can always spin up more instances if that's the issue. The stand-up continues. Each person reports. The product manager, Sarah, is working with the design team on a new layout for recommendation modules. They're testing different visual treatments to see what drives more engagement. The software developer, Marcus, is refactoring the feature engineering pipeline, making it easier to add new data sources, more modular, better tested. The technical program manager, Lisa, is coordinating with the supply chain team on a new initiative to incorporate inventory availability into the ranking algorithms. No point recommending products that are out of stock. The intern, James, is working on a fairly simple project, analyzing which product attributes are most predictive of high ratings. It's good work for learning the tools and the data, not mission critical but useful. Maya remembers being an intern, the nervousness, the desire to prove yourself, the feeling that everyone else knows so much more than you do. It gets easier. You develop confidence. You realize that everyone is just figuring it out as they go along. The stand-up wraps up at 9:20. People scatter back to their desks. Maya returns to her investigation. Now she needs to really dig in. Quantify the problem. Understand the scope. Propose a solution. This is the core of data science work. Not just finding problems, but solving them. She opens a fresh notebook, titles it, Frequently Bought Together, Cold Start Product Investigation, starts documenting her analysis step by step. This is important. Data science isn't just about getting answers. It's about showing your work, making your reasoning transparent, creating artifacts that others can review and build on. She writes a markdown cell explaining the context, what metric declined, when it started, what the initial hypothesis is. Then she starts pulling data, lots of data. This is where Amazon's infrastructure really shines. The company has invested billions in data systems. Redshift for data warehousing, S3 for data lakes, Athena for ad hoc queries, Kinesis for streaming data, EMR for big data processing, Glue for ETL, SageMaker for machine learning, all of it integrated, all of it scalable, all of it available to anyone who needs it. Maya writes a SQL query to pull detailed clickstream data for the Frequently Bought Together module over the last 2 weeks. She needs to see not just aggregate metrics but individual interactions. What products were shown, what products were clicked, what products were purchased, what the conversion rates were, all broken down by product category, by customer segment, by time of day, by device type. The query is complex, joins across multiple tables, filters on billions of rows, but Redshift handles it. That's what it's built for. The query runs for about 3 minutes, returns 50 million rows of data. Each row represents a single impression of the recommendation module to a single customer, whether they clicked, whether they bought, all the context. Maya downloads the results into a Pandas data frame. Pandas is a Python library for data analysis. Think of it as Excel on steroids. You can slice and filter and aggregate and pivot and plot, all with a few lines of code. It's one of the essential tools in every data scientist's toolkit. She starts exploring the data, creates visualizations, line plots showing click-through rate over time for different product categories. The pattern is clear. Electronics showed a sharp decline starting Monday evening. Home and kitchen showed a smaller decline. Everything else was stable. She creates a scatter plot. X-axis is product age, how long the product has been in the catalog. Y-axis is click-through rate on recommendations. There's a clear relationship. Newer products have lower CTR. Makes sense. The model hasn't had time to learn patterns, doesn't have enough historical data. She filters to just the new smartphone, creates a bar chart showing the 4 recommended products and their individual click-through rates. The phone case and screen protector have almost 0 clicks. The wireless charger has a normal click rate. The earbuds are slightly below normal. This confirms her hypothesis. The recommendations that are obviously wrong get ignored. The ones that are plausibly correct get some engagement. Now she needs to quantify the revenue impact. This is crucial. Amazon makes decisions based on business metrics. If you want to prioritize a fix, you need to show that it matters, that it's worth the engineering effort, that it will move numbers. She pulls purchase data. For customers who viewed the smartphone page, how many eventually purchased the recommended accessories? She compares the conversion rate for this product to the baseline conversion rate for similar products. The gap is substantial. For a typical smartphone launch, about 12% of customers who view the page eventually purchase at least one accessory. For this product, it's only 4%, an 8 percentage point gap. Now she does the math. The new smartphone page has been viewed about 5 million times since Monday evening. 8% of 5 million is 400,000. 400,000 customers who should have purchased accessories but didn't. The average accessory purchase is about $35. 400,000 times 35 is $14 million. $14 million in lost revenue over 48 hours. The number makes her heart rate increase slightly. She double-checks her calculation, makes sure she's not making an error. The number holds up. It might even be conservative. This doesn't account for the longer-term effects. Customers who had a bad experience and might shop elsewhere next time. Customers who bought fewer items overall because the recommendations weren't helpful. Maya writes up her findings in a document, not just numbers but narrative, explaining what happened, why it happened, what the impact is. She follows Amazon's document format, starts with a 1-page executive summary, then goes into details, analysis, data, visualizations, recommendations. For the recommendations section, she proposes a solution. The system needs to detect when a product is new and doesn't have sufficient historical data. In those cases, it should fall back to content-based filtering instead of collaborative filtering. Content-based filtering looks at product attributes. What category is it in? What are its technical specifications? What tags describe it? Then finds products with similar attributes. For a smartphone, content-based filtering would look at things like screen size, operating system, connector type, release date, then recommend accessories that are explicitly compatible. Phone cases designed for this specific model, screen protectors in the right size, chargers with the right connector. It's more reliable for new products, less sophisticated than collaborative filtering in some ways, but more robust. She outlines the implementation plan. First, they need to build the content-based filtering model. That's primarily a data science task. Maya can lead that. Then they need to integrate it into the production system. That's primarily an engineering task. Chen can lead that. Then they need to create logic to decide when to use which approach. If a product has been in the catalog for less than 2 weeks or has fewer than 1,000 views, use content-based filtering. Otherwise, use collaborative filtering. Finally, they need to test everything with an A/B test to make sure it actually improves the metrics. She estimates the timeline. 1 week for model development, 1 week for integration, 1 week for testing, 3 weeks total. It feels slow. $14 million every 2 days. But rushing would be worse. Deploy something broken, and you make the problem bigger. This is the constant tension in tech. Speed versus quality. Bias for action versus insistence on the highest standards. You have to balance both. Maya finishes the document, reads through it one more time, makes sure the logic is clear, makes sure the data is presented well, makes sure there are no typos or errors. Then she sends it to Rajesh and the rest of the team, pings them on Slack. Root cause analysis for CTR decline is ready. Document in your inbox. Too long, didn't read. New product launch broke collaborative filtering. Need to add content-based fallback. Revenue impact approximately $14 million over 48 hours. The Slack channel explodes. People reacting with emojis. Eyes emoji, fire emoji, sad face emoji. Rajesh responds immediately. Great work. This is exactly what we needed. Let's have an emergency meeting at 2 p.m. to discuss the fix. I'll invite Sarah and the engineering leads. We need to move fast on this. Sarah, the product manager, chimes in. $14 million. This is P0. Highest priority. Whatever resources you need, you've got them. Chen responds. I can start on the integration work today. Maya, let's sync after lunch to align on the interface between your model and my inference service. This is how it works at Amazon. You find a problem, you quantify it, you propose a solution, people mobilize, things happen quickly. There's a sense of urgency, a bias for action, but also a commitment to doing things right, to testing, to measuring, to learning from data rather than opinions. Maya checks the time. 11:30. She's been so absorbed in the analysis that she lost track. Her stomach reminds her that she hasn't eaten anything except coffee since waking up. She should get lunch before the noon meeting with Rajesh. She heads to one of the cafeterias. Amazon has several, scattered across different buildings. They serve free food during certain hours. Breakfast and lunch for all employees. It's a perk, but it's also strategic. Keep people in the building. Make it convenient to work through meals. Reduce the friction of daily life so you can focus entirely on the mission. The cafeteria is on the second floor, a large open space with floor-to-ceiling windows, long tables, high chairs, a servery with different stations, salads, hot entrees, sandwiches, beverages, everything designed to be fast and efficient. Grab food. Sit down. Eat. Get back to work. Maya goes through the line, grabs a grain bowl with vegetables and chicken, a sparkling water, an apple for later, finds a table by the window. The rain has started again. People on the street below hurrying along with umbrellas. She watches them for a moment. All those lives, all those individual trajectories, everyone going somewhere, doing something. She eats quickly while scrolling through email on her phone. More messages have accumulated. Questions about previous projects. Invitations to collaborate on new initiatives. A request to review someone's design document. The information flow never stops. You have to develop filters. Learn what requires immediate attention and what can wait. A colleague from another team sits down across from her. David. Works on search ranking. They've collaborated on a few projects. He's smart, easy to work with, curious about other people's problems. Hey, Maya. How's it going? Good. Busy. Just spent the morning investigating a model performance issue. New product launch broke our collaborative filtering. Ah, the classic cold start problem. How bad? Bad. 14 million in lost revenue over 2 days. David whistles. Ouch. You have a fix? Working on it. Going to add content-based filtering as a fallback for new products. Should be deployed in a few weeks if testing goes well. Makes sense. We had a similar issue last year with new search queries. No historical data. Model couldn't rank results effectively. We ended up building a hybrid system. Use behavioral signals when available. Fall back to text matching when not. This is one of the best parts of working at a big tech company. You're surrounded by people solving similar problems. You can learn from each other, share insights. The problems at scale have common patterns: cold start, drift, sparsity, latency, reliability, different domains, same underlying challenges. They chat for a few more minutes. Then David heads back to his desk. Maya finishes her food, checks the time. 11:55. Perfect timing for her meeting with Rajesh. She heads back to the 7th floor, finds an empty conference room, joins the video call. Rajesh is already there. His video feed shows him in another conference room, probably meeting with someone else before this. Hey Maya, good work on the analysis. The document was excellent. Clear problem statement, good data, reasonable solution. Exactly what we needed. Thanks. I think the approach is sound. Content-based filtering for cold start products, collaborative filtering for everything else. We'll need to tune the threshold for when to switch between them. But that's something we can optimize based on A/B test results. Agreed. Walk me through the implementation plan. What's the critical path? Maya shares her screen, pulls up a diagram she sketched in the document, shows the data flow. Input is a product ID. First check, is this a cold start product? If yes, run content-based filtering. If no, run collaborative filtering. Both models output a ranked list of recommended product IDs. Pass those to the rendering service. Display on the page. The content-based model is the main new component, Maya explains. We need to create product embeddings based on attributes, category, brand, technical specs, user tags, whatever signals we have about what the product actually is. Then find nearest neighbors in that embedding space. Have you built something like this before? Similar. I did a project at my last company using word embeddings for content recommendations. Same basic idea, different domain. I'm confident I can get something working. How long? If I focus on just this, probably 3 or 4 days to have a prototype, then another few days to optimize and validate. Call it a week total. Okay, make this your top priority. Drop everything else. I'll reassign your other projects temporarily. This is too important. They discuss a few more details. How to evaluate the model offline before deploying. What metrics to track. How to structure the A/B test. Then the meeting ends. Maya has her marching orders. Build a content-based recommendation model. Fast, but also correctly. No cutting corners. She returns to her desk, opens a fresh notebook, titles it Content-Based Product Recommendations, Cold Start Solution. Starts with requirements. What does the model need to do? Take a product as input. Output a ranked list of complementary products. Rank based on attribute similarity. Focus on compatibility. If recommending accessories for electronics, make sure they actually fit. First, she needs product data. Lots of it. The full catalog with all available attributes. She writes a SQL query to pull this from the product database. The query takes 5 minutes to run. Returns 100 million rows. 100 million products. Each row has dozens of columns. Product ID, title, category, brand, price, dimensions, weight, color, material, technical specifications, user-generated tags, bullet points from the product description. She samples the data, looks at a few rows to understand what she's working with. The data quality is variable. Some products have rich, detailed attributes. Others are sparse, missing values everywhere, inconsistent formats. This is the reality of real-world data. It's messy. You have to clean it. She writes data cleaning code, handles missing values. For numerical attributes like price or weight, she fills in with the category median. For categorical attributes like color or brand, she creates an unknown category. She standardizes text fields, removes special characters. converts everything to lowercase, lemmatizes words to their root forms. Then she needs to create embeddings, transform each product into a numerical vector, a point in high-dimensional space. The dimensionality depends on how many attributes you're encoding. She decides to use a combination of approaches. For categorical variables, one-hot encoding. For text fields, TF-IDF vectorization. For numerical variables, standard scaling. She writes the code methodically, tests each step on a small sample before running on the full dataset. This is important when working at scale. A bug that's invisible on 1,000 rows becomes catastrophic on 100 million rows. Better to catch it early. The feature engineering takes the rest of the afternoon. By 5 o'clock, she has a clean data set, 100 million products, each represented as a vector in a space with about 5,000 dimensions. Now she needs to find neighbors. For any given product, which other products are closest in this space? This is a nearest neighbor search problem. There are efficient algorithms for this. KD trees, ball trees, locality-sensitive hashing. But at 100 million points in 5,000 dimensions, even efficient algorithms are slow. She decides to use Face. It's a library developed by Facebook for similarity search at scale, specifically designed for this kind of problem. She loads her product vectors into Face, builds an index. The indexing takes about 10 minutes. Then she tests it, queries for neighbors of a random product, a laptop. The nearest neighbors are other laptops with similar specs, different brands, different prices, but similar screen sizes, similar processors, similar RAM. Good. The embeddings are capturing meaningful similarities. She tries another product, a kitchen knife. The nearest neighbors are other knives, chef's knives, paring knives, bread knives, also cutting boards, also knife sharpeners, products that are related by function, by use case. This is exactly what she wants. Now she needs to adapt this for the specific use case. She's not just finding similar products, she's finding complementary products. Products that people buy together. That's a subtly different problem. A laptop and a laptop bag are complementary, but two laptops are not. Two laptops are substitutes. She thinks about how to encode this. One approach is to use co-purchase data. Look at historical patterns. When customers buy product A, what else do they buy? Build a co-purchase matrix, then use that to weight the similarity scores. Prioritize products that are similar in attributes and frequently bought together. But wait, that's just adding collaborative filtering back in, and the whole point of this model is to work when you don't have historical data. When the product is too new to have co-purchase patterns, she needs a purely content-based approach. She decides to use category relationships. Products in complementary categories are more likely to be good recommendations. If someone is looking at a camera, products in the camera accessories category are complementary. Products in the cameras category are substitutes. She creates a mapping of category relationships. This category pairs with that category, manually curated based on product taxonomy. It's not perfect, but it's a reasonable heuristic. She incorporates this into her model. When finding nearest neighbors, she applies a penalty to products in the same category as the query product. They might be similar, but they're not complementary. She applies a boost to products in known complementary categories. She tests the updated model, queries for the new smartphone that caused all the problems. The nearest neighbors now include phone cases specifically designed for this model, screen protectors in the right size, chargers with the right connector. Much better than the collaborative filtering results that were showing accessories for old models. Maya feels satisfied. The model is working. Not perfect. There will be edge cases, products that don't fit the pattern, but it's a huge improvement over what they have now, and it's designed to handle cold start situations. Exactly what they need. She checks the time. 7:15. later than she intended to stay, but she wanted to get to a good stopping point. Tomorrow she'll continue optimizing, make the inference faster, handle more edge cases, document everything, prepare for the emergency meeting to discuss the fix. She saves her notebook, commits her code to the internal repository, writes a message describing what she did, then closes her laptop. The office has emptied out, only a few people still at their desks. The lights are dimmer, the energy is different. Maya packs up her backpack, heads to the elevator, rides down to the garage, gets in her car. The drive home is slower than the morning. Traffic is still heavy even at this hour. Seattle's tech boom means the roads are always crowded. Everyone working late, everyone going somewhere. She thinks about the day as she drives, the problem she found, the analysis she did, the model she built, the impact it will have once deployed. Millions of customers will see better recommendations. Will find products that actually work for what they need. Will have a better shopping experience. And Amazon will recover that lost revenue. Win-win. That's what she loves about this work. The tangible impact. It's not abstract. It's not theoretical. Real people are affected by what she builds. Real businesses depend on her models. For better or worse, she's shaping how commerce works in the 21st century. It's a responsibility, but also a privilege. She arrives home around 8 o'clock, changes into comfortable clothes, makes dinner, pasta with vegetables and grilled chicken. Simple, but satisfying. She eats while watching a documentary about ocean ecosystems, something completely unrelated to work, giving her brain a rest, letting the problems percolate in the background. After dinner, she does a bit of reading, a research paper on recommendation systems that someone posted in one of the Slack channels. It's about using graph neural networks to model relationships between products. Interesting approach. Might be worth exploring for future work. She bookmarks it. Around 10:30, she checks her work email one last time, just to make sure nothing urgent came up. There's a message from Chen. He reviewed her notebook. Has some questions about the model architecture. Wants to sync tomorrow morning to discuss integration details. She responds briefly. Confirms she'll have time at 9:30 before stand-up. She brushes her teeth, sets her alarm for 6:30 tomorrow, gets into bed. The rain is falling again, steady and rhythmic against the window. The sound is almost soothing once you get used to it. As she lies there waiting for sleep, Maya thinks about tomorrow. The emergency meeting at 2 p.m., presenting the solution to stakeholders, getting buy-in, starting the implementation. There will be challenges. There always are. Unexpected technical issues, integration problems, trade-offs to navigate. But she's done this before. She knows the patterns, knows how to move work forward at a large company. And somewhere out there, right now, millions of people are shopping on Amazon, clicking on product pages, seeing recommendations, making decisions. Some of them are seeing bad recommendations because of the bug she identified. But soon, if everything goes according to plan, they'll see better recommendations. They'll find what they need, and Maya will be able to see it in the data, those clicks, those purchases, those small confirmations that the work matters. That's the promise of data science at scale. Every click represents a person. Every conversion represents a need being met. Every dollar of revenue represents value created and captured. And somewhere in the vast complexity of it all, there's meaning. There's impact. There's the satisfaction of knowing your work made someone's life a little bit easier, made a system a little bit better, moved humanity forward by some small increment. Maya closes her eyes. Tomorrow will come soon enough. Another day, another data set, another problem to solve. But for now, there's rest, there's quiet, there's the peaceful darkness where no emails arrive and no metrics decline and no models drift. Sleep comes gradually. Her breathing slows. Her mind quiets, and across the world, in data centers humming with activity, her previous models continue running, making predictions, serving recommendations, operating autonomously. The work she did yesterday and last week and last month, all crystallized into algorithms that execute millions of times per second. That's the beauty of software. You write it once, it runs forever, or until something breaks. Your effort multiplies, your impact scales. One person can affect millions. One insight can move billions of dollars. One line of code can change how the world works. The night deepens, the city sleeps, but Amazon never does. 24 hours, 7 days, 365 days. The platform runs continuously. The data flows continuously. The models predict continuously. And tomorrow, Maya will wake and do it all again. Find problems, analyze data, build solutions, ship code, make impact. That's the rhythm. That's the cycle. That's what it means to be a data scientist at the world's largest online retailer. To work at a scale most people can't even imagine. To wrestle with problems that don't exist anywhere else. To constantly push the boundaries of what's possible with data and algorithms and computation. And as she drifts into sleep, the last conscious thought Maya has is gratitude for the opportunity, for the challenge, for the chance to work on problems that matter, to build things that millions of people use, to be part of something larger than herself, to contribute to the vast, complex, ever-evolving system that connects buyers and sellers across the globe. The story continues tomorrow, and the day after, and the day after that, because the work is never finished. The models can always be better. The insights can always be deeper. The impact can always be greater. That's what keeps you coming back. That's what makes it worth it. The endless fascination of turning data into understanding, patterns into predictions, insights into action. Sleep now, rest well, dream of algorithms and optimization, of A/B tests and statistical significance, of the million ways that data shapes our world. And when morning comes, the cycle begins again. Fresh data, fresh problems, fresh opportunities, always more to discover, always more to learn, always more to build. The end for tonight, but tomorrow, it all begins again.